All right, welcome to The Explainer. Today, we are diving into one of the biggest puzzles in tech. We're talking about how to take these incredible, powerful, large language models, these AI giants, and make them not just smarter, but also smaller, faster, and, crucially, safer for everyone. Let's get right to it.
So, we've built these digital giants, right? They can write code, they can write poetry, they can reason in ways that are just mind-blowing. But their massive size makes them super expensive, kind of slow, and honestly, pretty hard to control. Which leads us to the big question for today. How do you actually tame one of these things for the real world?
Well, it all starts with understanding what we call the giant's dilemma.
At the very core of this whole problem is this critical trilemma that every single developer is wrestling with. You're trying to juggle three things at once. You want top-notch performance, you need to handle massive scale, and you have to optimize your resources so you don't go completely broke. It's this constant tension that is really driving all the amazing innovation we're about to talk about. So where do we start? Well, the first piece of the puzzle is what you might call an inside job. We have to go in and optimize the AI model itself. It's all about making that giant a lot leaner and a lot meaner. And the first technique here is something called parameter efficient fine-tuning, or PEFT for short. Now, the idea is so simple, but it's absolutely revolutionary. Instead of retraining an entire, say, 100 billion parameter model every single time you want to teach it something new, PEFT lets you make these tiny, really targeted adjustments. This is a total game changer for cost and for speed.
And this analogy just hits the nail on the head. It really captures the elegance of what's happening. You're not doing a full-body overhaul on the AI. You're acting like a surgeon, making a precise targeted incision to guide all of its incredible knowledge toward a new specific job.
And the results? They are just staggering. I mean, look at this. Take a popular PEFT method called LoRa. When you apply it to a model like GPT-3, it cuts down the number of parameters you actually have to train by over 99.97%. Just let that sink in for a second. You are updating less than 0.03% of the model. And you often get performance that's just as good, or sometimes even better than if you'd retrained the whole thing. That is just incredible efficiency. Now, what if we could take that a step further? Well, that's exactly where QLoRa comes in. It takes LoRa's targeted tuning and adds another amazing trick called quantization, which basically means you're compressing the entire base model into a smaller format. The result? A memory footprint that is just drastically reduced. So much so that you can fine-tune a huge 65 billion parameter model on a single affordable consumer GPU. This really opens up AI development to so many more people. And that technique we just mentioned, quantization, it's not just for fine-tuning. It's an incredibly powerful tool all on its own. So beyond just tuning, we can use it to directly compress the model, making it way more efficient for just everyday use.
But here's the catch. It turns out there's no single best way to compress a model. The right choice completely depends on the job at hand. So for something like an interactive chatbot, where you need those fast, snappy answers, you'd probably use something called weight-only quantization. But if you're processing massive batches of text offline, you'd go for full quantization to squeeze out every last drop of computing speed from your GPU.
Okay, so we've optimized the model itself. The inside job is done. But that's really only half the battle. Now we need the outside job. We need an intelligent system to manage that model out in the wild.
This brings us to a really cool concept called a meta-ML layer. And honestly, the best way to think about it is as an air traffic control system for your AI. The goal isn't just to run one big, powerful model anymore. It's to have a smart system that can orchestrate a whole fleet of them, big and small.
And a huge part of this air traffic control is something called intelligent routing. It works like this. A user's query comes in. Instantly, a tiny, super fast classifier model looks at it and asks one simple question. Is this easy or is this hard? If it's easy, boom. It gets sent to a small, fast, cheap model. If it's complex, it gets routed to the big, powerful, expensive one. By always using the right tool for the job, you save a ton of money and a ton of time.
But look, an efficient system is only one part of the equation. It absolutely has to be a safe one too. And this brings us to one of the most critical operational challenges out there: building effective guardrails.
Guardrails act like a dynamic external defense system for the AI.
They basically sit around the main model and they watch every single input and output. They're there to stop jailbreak attacks, to filter out harmful stuff, and to enforce safety rules. And they do all this without ever having to change the core model itself. You know, this has really become a constant arms race, requiring dynamic, sometimes even AI-powered defenses just to keep up with all the new threats.
And that leads us to our final operational challenge, which is the problem of hallucinations. How do we make sure our AI isn't just, well, making stuff up? We need a way to check its facts, and we have to be able to do it at a massive scale.
So how do you solve that at scale? Well, the solution is just brilliant. You don't use another giant, expensive model like GPT-4 to fact-check your first model. No way. Instead, researchers have built these small, specialized models like MiniCheck. And it can verify facts with pretty much the same accuracy, but look at this chart. It does it at a cost that is up to 400 times lower. All of a sudden, making AI trustworthy is actually affordable.
Okay, so we've looked at the inside job, optimizing the model, and the outside job, building smart operations around it. Let's pull all these pieces together. And this brings us to what I think is the single most important takeaway. Model optimization and smart operations, they are not separate things. They're a symbiotic loop. Making models smaller and more efficient, that's the inside job. That enables smarter strategies like intelligent routing. And then the real-world needs for speed and safety, that's the outside job. That drives the next wave of research into making models better. Each side feeds the other. And looking ahead, this loop is only going to get tighter. I mean, imagine hardware specifically co-designed to run these hyper-efficient models. Imagine AI systems whose only job is to manage and secure other AIs. We're moving towards these hybrid systems that will seamlessly blend the raw power of the cloud with the instant response of a device in your hand. Which leaves us with a final, kind of provocative thought to chew on. Maybe the goal isn't to build one single, all-powerful AI giant after all. Maybe the real future of AI is an intelligent, interconnected ecosystem of many models, some huge, some tiny, all working together, efficiently and safely. What do you think? Thanks for joining me on this explainer.